Polymer. Yeah. Thank you. Okay. Thank you for your attention.
Okay.
Sorry.
No, it's okay.
I must put it in advance that this presentation is a little bit out of field with respect to the others, but I will try to tailor it to drive your attention and to see if it can be of interest for you. So what I will present you today is a class of optical fiber sensors for monitoring different quantities in polymer materials. We focused on monitoring of moisture and chemical in polymers, but I will show you that it's possible also to sense different quantities. This is the outline of my presentation. So let's move to the aim of the work. We started this project because pipes for oil are made of glass reinforced polymers. This is the typical structure where you have a outer material which is electrical glass fiber reinforced vinyl ester, and the inner material is can be pure vinyl ester or vinyl ester reinforced with glass fibers. And when they work in hostile environments, in oil applications and so on, there is the problem of salty water diffusion, and there is also a problem of diffusion of some chemicals. And there are companies like the one we are collaborating. Its name is Element. It's based in London. They want to test these materials, and they want to perform real-time monitoring of during some aging tests. So they asked us to develop sensor for that. Of course, we are optical engineers, and we proposed fiber optics as a meaning to do this sensing. Why using fiber optic sensors? Because fiber optics, optical fibers have a small form factor. They are about 125 micrometers in diameter. And in our case, we use glass optical fibers, which can be integrated into the polymer matrix without producing any changes in the material behavior. Another benefit is the electromagnetic immunity, which can be a problem in some applications. I just saw the first presentation. They were using electrical sensors to sense the crack formation. In some cases, this can be sensitive to electromagnetic interference, which is not the case of fiber optics. And of course, you can do remote operation. You can have your measurement unit far away, kilometers from the sensing area. So, just to talk in brief, if you do not have a background on fiber optics and fiber optic sensors, an optical fiber is made of a glass core and cladding, and it can also be recoated with a polymer coating material. And the basic behavior of an optical fiber is that it guides light through the total internal reflection effect. So here you have depicted the scheme of the ray of light that is bouncing from at the interface in current lighting, so it propagates along the fiber. How do we make a sensor out of an optical fiber? We must change some feature of the guided light due to the sensing quantity. So we must find a way to modify the intensity or the wavelength or the polarization of the light. Okay? Due to the to the chemical or the physical quantity we want to measure. There are optical fiber sensors that are commercial for even for structural health monitoring application. Some works were also presented at this conference. I saw them. The standard commercial sensors in this case are fiber break ratings, if some of you is aware of this. And of course they work, but in our case, what was the problem? The first problem is that you can make them sensitive to chemicals, but this is not the normal way they work. But the most important is that in our case they are not disposable unless you are able to pay a lot of money to just throw away your sensors. So we developed some simple and disposable fiber optic sensors based on evanescent wave sensing, which I'm going to show you how they work. So what we have done, we take the fiber core and cladding structure. We etch the fiber at some point. So this means we remove the cladding, the glass cladding, by a chemical process. Basically, we use fluoridic acid. And when the fiber is embedded into the material, into the polymer matrix acts as a cladding, and the optical signal traveling, which extends somehow into the cladding of the fiber. Now the cladding is replaced by the polymer matrix, and any change in the polymer matrix will change some feature of the incoming light. In this case, there will be some changes in the intensity. So basically, with a source and a detector, it is possible to produce a low-cost sensing system. These are some pictures of the experiments we carried out. So you have the sample that you want to test. We embedded several fibers. As you can see, there is the input and output, and embedded into the Vini Lister sample, there is the etched section that is sensitive to the water diffusion. In this case, the samples were stressed, underwent the aging process in seawater at 120 degrees, 2 bars. In this case, 96 hours, but we made a lot of samples, a lot of experiments in different conditions. So we basically put this sample into this fixture. We have the boiling water and the transfer some time. And then we measure the diffusion of water into the material. The measurement setup, it's a standard source and detector arrangement. So you have a broadband source, in this case emitting in the infrared region. You have the sensing, you have the sample and the embedded fiber, and an optical spectrum analyzer that makes the spectral analysis. It's possible to embed, as you have seen in the previous picture, several fibers, but you need to do a multiplexing system both at the source and at the detector, which can be a little bit problematic. So, some results. We have embedded fibers into those samples, and we made different tests. Here you have an example of a sample where fibers are embedded at different positions through the thickness of the sample. And if you take, for example, one fiber in the middle, you can see that there is the transmitted signal that is dropping as the water diffuses into the polymer resin, into the vinyl ester resin. There are some details about published paper. And by putting those fibers at different positions, it's possible to see the rate of, to extract the rate of diffusion. Okay, so this basic way to sense the water diffusion works, but and it's also low cost because the sensor preparation is very easy. You basically etch the fiber, but there are some problems. First, etching and embedding are critical because you must etch the fiber somehow into the middle and later embed it. So there are the etched fiber is only 60 micron thick, and it's very fragile, very easy to break, and so it's quite. One must be quite skillful to do this operation. And as I said before, okay, I'll go fast. You have one input and one output, so multiplexing is difficult. So what we have conceived is a new kind of sensor, which is based on reflection. So we found a way to easily produce a mirror at one of the sensor tip. So the sensor can now work in reflection. You have the source, which emits light, then a part of this light is back reflected, and there is this component which it's a circulator that separates the forward from the back reflected light, and it goes again to the detector, the optical spectrum analyzer. So in this case you only have one connection, so you the problem of fragility is somehow solved. And the nice feature is the easy way we found to produce this mirror at the fiber tip. You could normally use some techniques such as metal sputtering, which work very well, but they are expensive, they are difficult to implement. We found this simple chemical reaction that is called toluene reagent. It's based on silver nitride, potassium hydroxide, and ammonia. And with a simple recipe, it's possible to deposit a silver on the fiber tip. It is you must just clip very precisely the fiber at the fiber tip, and it's possible to get a nice reflection from this fiber. So we basically made this new kind of sensor. We are making measurements, but the first results demonstrate that this kind of sensor work as good as the one I showed you in transmission. So it's a promising way. Just to conclude and to be more closer to this session, the formation and fracture at high strain rate. We can use those sensors for strain as well, because if you take the fiber tip and you bend it, it is very sensitive to strain. And of course, in our application, we embed the fiber, and we don't want the strain to corrupt the measurement of diffusion of water. But in some cases, I mean, it's possible to measure strain easily with this system. And what is the frequency of that we can sample? this is basically constrained by the equipment you are using. In our case, we can easily perform measurements at 1 kilohertz or even above. Okay, so the conclusion, we produced simple and cost-effective optical fiber sensors for measuring diffusion of water into polymer for oil application. We developed this single-ended reflective sensors that are easily to embed into the polymer matrix. We are working on engineering the tips, for example, depositing fluorescent polymers for detection of other chemicals. And of course, since we are this presentation comes into a fracture conference. As I said, it's possible to measure strain, deformation, and so on. And any feedback from you would be welcome. I just conclude that this project has been supported by this COACH consortium, a European project. And this concludes my presentation. Thank you very much.